Welcome to part 2 of the video tutorial for the 2008 Electricity and Electromagnetism exam. Question 2a, so this is on direct current electricity. How much energy does the battery give to each coulomb of charge? So what we have here is the battery, which is a 12 volt battery, and voltage itself is just the electric potential difference. It's not really, so voltage is kind of a product of other things, and it's the product of joules and coulombs of work done per charge, per coulomb of charge. So really it's giving 12 volts of voltage, so that means it's giving 12 joules per coulomb of charge. So the answer is just 12 joules. Show that the total resistance in the circuit is 6.56 ohms. Okay, so let's have a closer look at the circuit now. We've got 12 voltage battery, and we have this 4.5 resistor, which is by itself, it's in series. And then we have these two resistors here, which are in parallel. So we need to show that the total resistance is 6.56. So the resistance is going to be, the total resistance is going to be the parallel resistance plus the series resistance, which is just going to be 4.5 ohms. So we need to work out what the parallel resistance is. And this is on the formula sheet. So this is written as RT here, but it's R parallel effectively. That's what it's showing you. This is for parallel resistance, or when resistors are in parallel. So what you have to do is basically take 1 over the total resistance is going to be equal to 1 over the sum of the resistors. So when you invert it afterwards, you'll end up with a different amount than if you'd just added the resistors. Obviously it'll be rather different. So you can't just simply say, oh, it's 3.4, 5.2 and 4.5 and add them up. So what we're going to have here is 1 over RP is going to be equal to 1 over 3.4 plus 1 over 5.2. So 1 divided by 3.4 plus, plus 1 divided by 5.2 is equal to 0.4, that's a lot of stuff. But that comes to, if you press the fraction button on your calculator, which is this one here, or you could just use that amount and you'd probably get close to the answer. But remember, this isn't giving us the resistance, it's giving us 1 over the resistance. So it's giving us 215 over 442. And the fraction amount is obviously the exact answer, so it's better to give a fraction amount than rounding the decimal at this stage. So that means that if you flip it over, so you end up with this, then we have to flip this as well to get the actual resistance, and this is going to be 442, 215. How much is it? 215. So that gives us 2.06, which looks like what they're asking for. So this is equal to 2.06 3SF. And if we have a look here again, we have the 4.5 resistor, obviously. So this means that the total resistance, I'm running out of space a bit, but total resistance is equal to 2.06 plus 4.5, which is equal to 6.56 ohms. So we've shown that. Calculate the current through the 4.5 ohm resistor. So now we have the resistance for the entire circuit. Well, they gave it to us before. And we have the voltage. Then we can use Ohm's law to find what the current is. So I is equal to V over R, which is shown here. It's shown as V equals I over R, so obviously to find I, we just divide both sides by R. So it ends up like that. So I equals V over R, which is equal to 12 over 6.56. Which is equal to 1.83. 1.83 amperes. And remember, the current through the entire circuit is going to be the same, no matter which resistor you're looking at it from. And the way to think of this is that when you've got the charge coming around like this, from the positive to the positive, or positive to negative, when it encounters the resistors, it's obviously going to slow down. So, say if it's going really, really fast and then slows down all of a sudden, the charge coming behind it, or because really what's happening is electrons are flying around. So when the electrons are coming, they're going to be slowed down by the resistor, and that's going to cause a pileup. So really you can only move as fast as the slowest part of the circuit. So that means that the current is going to be the same all the way around. Hopefully I didn't confuse you too much there. The electrons, what's actually happening is the electrons are flowing from the negative to the positive, and that means that the positive charge is coming around this way. So when we think of circuits, the charge itself is coming from positive to negative, but the electrons, what's actually happening is electrons are going around. That's probably not helpful, but yeah. I show that the voltage across the 3.5, so yeah, this is 1 amperes. Show that the voltage across the 3.4 resistor is 3.8 volts. Okay, so now we know that I is equal to 1.83 amperes. And we need to show that the voltage across this resistor is going to be 3.8 volts. So that resistor is in parallel. So that means the resistance is going to be the same. You have to use the resistance for the parallel circuit, not just the resistor itself, because it's in parallel. So that means resistance is going to, and we worked this out before, it's 2.06. 2.06 ohms. And so now we just need to find what the voltage is at that place. So that means V is equal to I R, which is going to be 1.83 times 2.06. So that's going to give us, what should we round that to there? Well, yeah, 3.8, it tells us. So this is going to be 3.8 volts, because and the reason you use the current for the whole thing is obviously, like I said before, the current's going to be the same all the way around, but the resistance isn't quite going to be the same. For that, obviously we're looking at it across that resistor, so that you're just going to use the resistance of the parallel circuit, not including the entire circuit. So this is going to be, yeah, 3 point. If you get a different answer there, it would be a bit strange. State the voltage. Oops, there we go. State the voltage across the 5.2 resistor and give reasons for your answer. Well, if we can have a look at this diagram now, which is the same except. So the 5.2 resistor and the 3.4 are both in parallel, as we said. So, like with this one, how we had to use the parallel resistance, with this one we do as well. So the voltage across is going to be the same. So the voltage is going to be equal to, what was it, 3.8 volts? Because nothing's changed, we're using the same resistance and obviously the same current. So it is going to be the same. So the 5.2 ohm resistor, and 3.4 are connected in parallel. Oops. This means what does that mean? Well, the resistance will be the same. The parallel resistance will be used. Or the resistance from the parallel section will be used. Circuit will be used in both calculations. Oops. So the voltage will be the same. Across both of them. And this question here, they're adding a diode on, and diodes aren't in the new standards going from 2012 onwards for physics, level 2. So you don't actually, this won't come up in the exam or anything, but just to give you a brief, quick overview of what happens. So the way diodes work is that the current can only, they're one way, the current can only go through them one way, and that's shown by the current can only flow in the direction of the arrow. So in this one here, the current can only go this way. But as we see, the current or the charge is going this way, so it's going against it, and that can't happen. So that no current is going to flow through this diode, which means no current is going to flow through here. So that basically means that this, instead of being a 3.4 and a 5.2 ohm resistor in parallel, producing a resistance of 2.06 ohms, it's just going to be a 3.4 ohm resistor, which is in series. So for this question, how would the diode affect the current through the 4.5 ohm resistor? Well, the current is obviously the same through the whole circuit, as we said, but the resistance is going to be greater because the 3.5 ohm resistor in series is going to have higher resistance than it did in parallel with the 5.2 ohm resistor. So the total resistance goes up, and that means the total current goes down, so the current will fall. Calculate the heat energy produced by the 3.4 ohm resistor in 1 minute when the diode is connected to the circuit as shown in the diagram above. I guess I can do this, because this is a power question and those ones tend to come up. So I'll do the calculations for the current and everything now. So I is equal to V over R. R is going to be equal to 3.4 plus 4.5 now, which is going to be 7.9. 7.9 ohms. Voltage is still 12. So this is going to give us 12 divided by 7.9. So that's 1.52. So I is equal to 1.52 amperes. So we need to calculate the heat to energy produced. And there are probably going to be multiple ways of doing this. I think the easiest one, which makes the most sense, is to use power. So we know that P is equal to IV, and that voltage is equal to IR, because we want to be using the 3.4 resistor in our example. So we can just swap this out, and this is a pretty common rearrangement. You should have to do this in a lot of the exam questions. So if we have I times IR instead, right, when we substitute the IR for the V, like that, then that means that P is going to be equal to I squared, because we've got I times R. And if we substitute everything in, we've got a current of 5.2, so this is going to be P is equal to 1.52, all this squared, times the resistance, which is going to be 3.4. squared plus, times 0.4, so that gives us 7.9 if we round it correctly. So we've got power is equal to 7.9 watts, and power gives us, power is the rate of change, or the rate of work. So that means if we have 7.9 watts, that's how much energy is being done per second. And this is asking for 1 minute. So if we bring this back, we have 7.9 times 60, and that's going to give us 474, which is equal, 60p is equal to 474 joules. Looking back, I don't think we really should have rounded that early. I think it's probably much more accurate to use, because it was it was a it's kind of a marginal thing to round that. So if I just use that and times by 60, so that's probably a better, because that has changed our answer. So I'm going to put that in as 4.71 joules, which seems more accurate. Oh, they give it to us here. 4.71, 471 joules. And that's the end of question 2, so I'll do question 3 in the next video. See you soon.